So we have a few different flavors of reduction for alkynes. The first one is one that we've seen before with alkenes, and that is if we use the same conditions, so hydrogen and palladium on carbon, we get complete reduction of the triple bond. So what we saw for alkenes is if we have multiple alkenes, it will reduce both double bonds. What happens here is that we do get this intermediate alkene. So I'm going to add in hydrogens for a reduction. We get this alkene, but it doesn't stop. So it keeps going. We're adding in even more hydrogen to reduce all the way to the alkane. So the thing you want to remember for reduction of alkynes using palladium on carbon as a catalyst is that you get complete reduction. Okay, it's very difficult to stop at this alkene. Right, so for the next type of reduction, what if we actually do want to stop at the alkene? We do have some methods to do that, but they're not using hydrogen and palladium on carbon. We have to use a slightly different catalyst for this. Okay, so if we want to go from an alkyne and we want to form a cis alkene, we have a certain set of conditions that we can use to do that. So in this transformation, we have an alkyne here. We're going to use hydrogen gas and a new catalyst. So this is called a Lindlar catalyst. But what we get is a cis double bond. Okay. So let's figure out what this catalyst actually is. It's a mix of a few different things together. So the Lindlar catalyst it does have some palladium in there. So we have palladium, but we also have calcium carbonate, palladium acetate, and the last ingredient is quinoline. Okay, so quinoline has this structure. We have a fused aromatic ring that has a nitrogen in it. Okay, so that's quinoline. So all this mixed together, what it does is it poisons the catalyst. So in other words, it's a much less reactive catalyst, which allows us to stop at the alkene and not go all the way to the alkane. So it deactivates reduction of alkene. One thing that we notice is it is still a syn addition. Remember that the hydrogen first, that bond, that HH bond is broken and the hydrogens are bound to the catalyst. So when the double bond approaches, those hydrogens have to add from the same face. So that's where we get the cis double bond, or we could call it a Z double bond. Okay. So one more flavor. We know how to go all the way to the alkane. We know how to form a cis double bond, but we also need reaction conditions to allow us to form the trans. Okay. So this is trans double bond formation or transhydrogenation, and we're going to utilize some redox chemistry. So dissolving metal reduction. I like to call it electron soup since it involves a lot of transfer of electrons. For this, we're going to start with an alkyne, add in some sodium metal. So this is going to be the species that's giving up electrons. The reaction will take place in liquid ammonia, and it's going to be at low temperature. Okay, and we will get the E double bond, which is thermodynamically preferred, and we'll talk more about why that's more preferred in just a moment. In terms of mechanism, we want to see how this is actually working. So in the first step, we have our triple bond, and we have our sodium that has valence electrons on there, we know that sodium readily gives up an electron. So what we're going to do is we're going to break the pi bond, but instead of breaking it heterolytically like we've seen before, so heterolytically means that we're moving 2 electrons, we're going to break it homolytically, where we only have the flow of 1 electron. To do that, we're going to use a different type of arrow called a fish hook. So 1 electron will come from the sodium. Notice the difference in the arrow. We're going to split the pi bond, and 1 electron from that pi bond will go there, and the other one will be localized on the carbon. Okay. So when we do that, we did an electron transfer, and this is what we get. We have 2 electrons on this carbon now, so we have a negative charge, and then we have 1 electron on the other carbon of the double bond. This is called a radical anion, and if we think back to our pKa values, pKa here is going to be around 44. The next thing that we have in our reaction mix is ammonia. Okay, so another reason, very important to know our pKa values. Here our pKa is around 36, and what we're going to do is we now have an nucleophile, we have an electrophile, and the pKa difference is big enough for this deprotonation to happen. So we're going to take the electrons here, form a bond with hydrogen, and give those electrons to nitrogen. So from here, this is what we form. We now have this, and why don't we draw the hydrogen in a different color that we just added. So we have hydrogen there, and we still have this radical sitting here. The next thing is we still have more sodium metal around, and it has an electron on it. We're going to again give up an electron, and we're going to basically add those together. From there, we'll get this. Now we have a negative charge on this carbon, and it will do the exact same thing. We have more ammonia around. This is our solvent. We now have a nucleophile, a lone pair, form a bond with hydrogen, give those electrons to nitrogen. So what we get is this. And let's highlight the 2 new hydrogens that we added into our molecule. We have one here, and we have one here. So we also get plus 2 NH2 minus. The next thing we need to figure out is, okay, we formed a trans double bond with high selectivity. Why is trans more thermodynamically stable? And usually when we're asking this, we want to draw some orbitals. Okay, so why are we forming the trans double bond? Why don't we compare the cis and the trans and see which one looks more favorable? When we're forming that radical anion, we have something that looks like this. Let's look at the trans first. So that negative charge that we formed, we have it in an orbital here, and then the radical is right here. Okay, so this is our radical anion that we formed in the first step. Okay, and it's bouncing back and forth, but it's going to spend a lot more time in this direction. So this is the trans. Let's see what happens if we draw on the cis. If we have the cis, we get something that looks like this. We have radical there, and we have, should be a minus charge and a minus charge. Here, since this is filled, we now have 2 orbitals that have electrons in it that are too close. So what we get is some electron repulsion. So this is why the trans is going to be more thermodynamically stable. One other thing we can think about is something we've seen before with just thinking about the stability of a trans double bond versus cis. In this case, we also have some steric interactions because we have this methyl group and this methyl group that are very close to each other. So not only do we have the electron-electron repulsion, we also have some steric interactions that make it less favorable.